Hey there, I'm Ben Essex from the Empyrean Dynamics team. We're making drones smarter, safer, and easier to coordinate at scale.
I'm Justin Newkirk.
I'm Olivia Lillianquist.
I'm Ashton Stricker.
Hello, my name is Derek Chupp, and this is our lab.
About a year ago, one of our founding engineers, while working in industry at a military exercise with the United States Marine Corps, learned about a critical need for greater situational awareness of uncrewed airborne systems. The problem? First of all, drone operators could see information about the drone that they were flying, but no information about other drones in the air. Meanwhile, other folks on the ground had little way of knowing who the operator for a drone was, whether the drone was even friendly in the first place. As a result, in-air collisions and confusion and friendly fire are very much real concerns. A few months later, our team was formed, and we had a plan to address these problems. In fact, we had a plan to address the root problem: poor communication and coordination of drones at scale. Over the next several months, and with the backing of a firm working in this space, we developed a blended hardware-software solution that not only addresses these problems, but also to become an extensible foundation that will someday enable a collection of drones to complete user-defined tasks in a decentralized way with minimal user interaction. I'll turn it over now to Justin, who will show you how our product makes it possible for a single operator to control multiple drones.
In my hand now is the culmination of several months and many hundreds of hours of work. This tiny module easily plugs into a drone's flight controller, instantly joining that drone into a mesh network of all the nearby drones with one of our modules on board. Here we have a flight controller that acts as the brains of the quadcopter. To connect our module, we designed it to simply connect at the 4 quadrants, just like this here. This stack right here can then be attached to the drone itself. To just add a drone to the network, we're already done. One of the great things about our module is that it uses mesh networking with auto healing and auto routing. That means that as soon as our module comes online, it becomes a node in the network. Each drone we're connected to then contributes to the network, working to aggregate all the telemetry from all the drones and get commands from any drone, even at great range or beyond the line of sight. If we want to control the drones now, as a drone operator, we can begin by plugging any of our modules into a computer. Now let me show you how a drone operator would interface with multiple drones from our terminal user interface, or the TUI. And to show you guys how we connect to our module and how we control our swarm, we've set up a little demo here. What you're seeing right now are 2 of our modules connected to 2 drone flight stacks. This one right here will be acting as our ground control station, or basically the one that a Marine or whoever would then connect to control the swarm. This one right here actually acts as a real-life drone, and we're tapped into the flight controller here, so you can see it is live. Cool. So right now we're connected to our ground control station, which we can do through any terminal TUI software. And right here you can see that we can see from the drones their live data. Right now we're in a big metal building, so it just shows zeros. But that is, we get to see their uptime, their altitude, and all that jazz. Previously, all we had available in the past was just this piece of software. So if you wanted to see where all the drones were, you'd have to have like N number of computers for N number of drones, and that was awkward. Now, over here, we'll show you how we can connect to these drones and command them. So the first thing I'll try to do is send this guy over here a command to loiter. Now what I'll do is I'll type our loiter command, then I'll tell it that we're connecting to a single individual, and then we'll send it. Boom. Okay, so as you can see, the drone now realizes that it is in loiter mode, and if it were attached to a power base with motors, it would absolutely go. And then some other demos of that. Auto, this would actually send it on an auto mission. So that is the drone recognizing that time to do a mission, I am off, goodbye, which is pretty exciting stuff. Additionally, we can even put drones into groups, and we can even tell drones to fly. So that other guy, he was in group 2, so I'll put him back into loiter, but I'll do it from the group perspective. And since he's in group 2, I'll send it that way. Awesome. There we have it. So some other commands that we have available, all the basic ones, arm, loiter, auto, but we can also give each drone their own persistent call sign so that we can, at boot up, we can know exactly which drones are which is pretty helpful. That just kind of scratches the tip of the iceberg, but that's a lot of our functionality.
Now let's transition to demo our Mission Planner integration. So Mission Planner is the desktop application which is used to program missions to the flight controllers that we are using. So our software package, as you can see right here, talks to Mission Planner, which I will demo right now. So we can create missions by typing mission create, and then we'll give it a name. We'll say testing, and we'll see that mission is created. We can see what missions are currently saved on the computer. You see there's 3 of them. We can load specific missions by typing in mission load and then give it the ID number. And so we'll load up testing, which is the mission we just created. You can see that there's currently 0 waypoints saved on the mission. Now, moving on to the mission planner, we can connect to the drone. And once we have a mission, as you can see here, I've dropped a couple waypoints. We can click this right button and, hold up a quick second. We'll type in mission download to begin the download process. So you can see here, we are now waiting for missions to come in. So once we click the right button, we'll see that Mission Planner is telling us we're writing waypoints. We can see on their terminal GUI is getting updated, the waypoints as they get written. And then once we're done, you'll see the download complete. And now if we type in mission status, we can see that we've programmed 7 missions. We also are able to send missions across the radios. However, I'm not going to be demoing that right here. But yes, that is our mission plan integration.
One key feature that has our customers really excited is our integration with a piece of situational awareness software that is incredibly common in the military and increasingly used for emergency response called TAC or TAK. While we don't have time to demonstrate that feature for you in this video, you can learn more details on our website, empdyn.com or empdyn.com. Now we'll go back to Ben to discuss some of the technical details of our effort.
We are, as you can see, primarily an embedded systems project with the vast majority of our code written in C for the PIC32 microcontroller. For testing our code, we use Seedling, a build system for C projects that uses CMOC, Unity, and C exception. Our debugging tools consisted of oscilloscopes for reading electrical signals, software-defined radios for profiling our radio signals, and other various specialized tools for debugging our embedded systems. We extensively use Git for our software version control and GitLab for our project management. We also built and provisioned a continuous integration, continuous development pipeline to automatically test and build our code and save the artifacts from functional builds, which was a significant feat for an embedded systems project. Over the course of the capstone project, we completed 287 issues, 81 merge requests, and 7 repositories with a mixture of C, Python, and Rust developed in 3 different operating systems. By the final release, we had 72 unit tests, over 1,000 commits, over 25,000 lines of code that we wrote, and thousands of combined hours working on the project. Moreover, the project was heavily resource constrained in terms of both processing power and available memory due to its use of a microcontroller compared to other computer science projects, for example, a web app or a desktop application. In particular, the project had a single core running at 200 megahertz with at most 2 megabytes of program memory and 512 kilobytes of storage. As a result, our code needed to be as efficient as possible in terms of both time and space. Thanks for watching. We're excited to put our product to use, making drones smarter and safer for all.